In this video, we're going to see how to simulate the dynamics of two correlated stocks. Maybe we know that they belong to the same sector, so we must be able to model this relationship. Let's see how we can do it. Let's start by importing the libraries that we will need. So NumPy. Then from SciPy we import stats and pyplot. Then we can set a random seed so that you can get the same results as I do. Now let's start to see how the parameters of our simulation will look like. Let's say we want to model two stocks, X and Y, where X at time 0 has a value of 20, while Y at time 0 has a value of $30. Then the volatility of these two stocks will be 0.4 for the first stock and 0.3 for the second stock, or the Y stock. Let's say the interest rate is 2%, and we want to make this simulation on a time horizon of 2 years. And we want to divide our time horizon in 1,000 time intervals, so that we can define dt as t divided by n. And we will make one simulation for each stock. Then we define tt as an object that starts at 0, stops at t. We add this small increment so that the t will be included in our object with a step of dt. Then n is the length of tt. Then we create the x and y objects. So np0 with a shape of n rows and just one column, so we can put the m here. Then the same thing for the y stock. Okay, and we also want the first elements of x and y to be equal to x0 and y0, as we said before. Now we have to create our random component of the simulation, our dv. We do that using this command, stats.norm.rvs, with size equal to n-1, because we want to have n-1 random values, as the first element is already defined and it is x0 and y0, so that is excluded. And we want two columns, one for each stock, so we can put m multiplied by 2. Now that we have also our random component, we can start our loop for I in range n-1. We put n-1 here for the same reason we put n-1 in the dev, in the random component. So x, let's write first the dynamic of x, and here we should also multiply by the square root of dt. So equal to x I So if you remember the formula of the geometric Brownian motion, here we must have r minus 0.5 volatility squared multiplied by dt plus vol multiplied by dv. And we want to take the first column, so we put a 0 in here. And also, we also put a 0 in the volatility to capture only the first value of volatility associated with x. So let's write the same thing also for y, but we will have to make a small adjustment on the stochastic part. We will see how. So this part remains the same. We have to obviously change the volatility here to 1. And for this component, let's say the correlation between the two stocks is equal to 0.5. We will use this formula, the formula that you can see here, to write this new component. So here we have the random component for the previous dynamic. We must multiply it by the correlation coefficient. Then we must add this quantity, the square root of 1 minus rho squared, and we multiply this by the random component associated to the second dynamic. So here we have the formula for our correlated dynamics. Let's run all of these. Let's see if it works. Okay, everything seems right. Let's see how the graph looks. plt dot subplots. Then we plot on the x-axis we want tt and x. Then we put a label that is stock x. We do the same thing for y. So we want to write a title that is correlated stocks. And we also want an x label that is time, and a y label that is price, stock price. Then we add a legend and we display the results. So let's see our graph. And this is the result of our simulated dynamic. As you can see, we have stock x and y that display a quite noticeable correlation, and we see that they move quite differently for the different values of volatility we gave them.